All right, welcome everyone. Happy Thursday, and thank you so much for joining us today. My name is Zach Semke, and I am director of Passive Accelerator, and I'm super excited to have you here, and also have Mike Cairns join us from Innotech Windows and Doors for this presentation, this special component spotlight, Triple-Pane Windows, and a look beyond U-values. Now to the heart of the program with Innotech Windows and Doors and Mike Cairn. So Mike brings 3 decades of construction and fenestration experience to his role at Innotech. His combined technical expertise, hands-on experience, and passion for sustainable construction ensure the windows and doors in every project are engineered and installed to exceed each project's performance requirements. Mike is a certified Passive House tradesperson, the chair of the HAVAN, the Vancouver Home Builders Association, its education and technical committee, as well as its technical advisory group, a member of the Fenestration Canada Pacific Chapter Group, and an instructor of windows and installations for the High Performance Building Lab at the British Columbia Institute of Technology. So I'm about to hand it over to Mike, but as questions occur to you during Mike's presentation, please type them into chat. And we have Sean St. Amour here to play the role of Q&A concierge. And so he'll be moderating that conversation, and you'll have a chance to ask your questions directly of Mike. So with that, Mike, please take it away.
Okay, awesome. Thanks, Zach. I'm gonna just dive right into it. Share my screen. Okay, can everybody see the presentation? Thumbs up?
Yes.
Perfect. Thank you very much. Okay, it's great to be back here on Passive Accelerator. Thanks for the intro, Zach. Triple-pane windows, looking beyond U-values. That's the topic at hand. Clicking through. So when we look at windows, there's really only 2 things that matter: U-values and solar heat gain. And all of the evaluation systems are the same, so we can easily compare windows and doors. You know, just take a look at the U-value, select the lowest, and specify it for every project. I mean, of course, that was maybe a healthy dose of sarcasm. Evaluating and specifying windows and doors is complicated, but you know, somehow the industry can get a little bit stuck on those oh so trendy U-value or solar heat gain values. But before jumping into the topic, to introduce myself, you know, beyond Zach's fantastic intro there. So my name is Mike Cairns, and I am the Business Development Manager at Innotech Windows and Doors. And Innotech is a Canadian manufacturer of high-performance fenestration, including PHI certified windows and doors. We've been doing it for over 2 decades, locally testing, manufacturing, and installing windows and doors for highly sustainable projects of many different types. Our products are typically specified for custom homes, low to high-rise multifamily housing projects, affordable affordable living, senior housing, hotels, schools, office buildings, kind of running the gamut. The majority of the projects we supply have a clearly defined performance target, whether that's acoustic requirements, air tightness, water resistance, thermal performance, etc. Of course, many of those are passive house, including both FIAS and PHI. And a few recent or live examples include Parkview at Terwilliger Plaza in Portland, 11-story high-rise, 127 independent living apartments for seniors, 370,000 square feet. This senior living high-rise is the largest FIA-certified senior living building in the U.S. and the largest passive house structure on the West Coast. Timber and Harmony at Brightside is an affordable senior housing development that features 2 buildings, 157 total units in Vancouver, BC. Couple of exciting projects we're going to be supplying next year. This one is Vienna House in Vancouver. That was ongoing right now. Very cool. Affordable housing development targeting PHI certification, featuring prefabricated construction, mass timber. Kinder Construction recently posted some great progress videos, and Sean's, as always, has tons of content on everything. I don't know how he gets around some as much as he does. And we're excited about this one as well. A 17-story social housing project built with mass timber, targeting PHI certification. ZGF architects can do construction. Very cool stuff to see, uh, especially in our local area for myself. So back to the topic at hand, U values. In the quest for low U values, have we lost sight of what they mean, how they're calculated, and their importance when evaluating and specifying windows and doors for high performance projects? Given our niche market, we know U values. In fact, we'd like to think that our U values are fairly impressive. But time and time again, we will hear the following: manufacturer X has a lower U value. Well, do they really? Maybe, maybe not. Let's take a look. So our goal with any high performance building is to limit the thermal loss from the inside of the building to the exterior. Heating or cooling the buildings, we don't want to heat or cool the outside at the same time. The U value is measuring the heat flow through the window. So the lower the value, the better, because that means less heat is flowing through. The UW, the window value, measures the insulating value of glazing, glazing edge, and frame. UW installed includes the installation value. We'll chat a bit more about that later. So first things first, we do need to understand U values and how they're determined. Here in North America, we may encounter 3 different ways to calculate U values. So those systems have different surface films, different boundary conditions. They follow different methodologies for calculating U values. Note in here, so we've got in NFRC, which is the North American system, it actually references an ISO standard for calculation, but a different one than what the Europeans use. It's a very comprehensive calculation procedure based on heat transfer relationships solved using numerical methods. And it also uses, of course, these different boundary conditions. So we're talking 0 degree Fahrenheit, minus 18 Celsius, up to 21 Celsius, which is 70 degrees Fahrenheit as the interior temperature. So it's a very broad temperature range compared to the typical European ISO, which is 0C or 32 Fahrenheit up to 20C, 68 Fahrenheit. And then Passive House has a very similar system to ISO with some slight variations and different boundary conditions again. So we're going with a frame evaluation at minus 10C, which is 14 Fahrenheit. And the IGU is actually evaluated, depending on what climate it's evaluated in, down to minus 7C or 20 Fahrenheit. So there are some differences in there, and they will alter the effect when we thermally simulate. Another thing to note is that NFRC evaluations are always whole window. They are looking at a fairly complicated window, but they are taking a specific glazing configuration in the frame all at once. So that's, you get one number for that product. ISO, of course, the procedure, it simulates the U value by putting a standardized panel, a calibration panel at 0.035 watts per meter Kelvin. And it standardizes the conditions. You get your U frame value, you get your glazing edge value, you get your glazing value, you get an installation psi value, and all of those different parts are put together in the final product. And when we talk about solar heat gain, interestingly, it's also evaluated differently based on NFRC, ISO, or PHI. So they have different boundary conditions. So the exterior temp is going to be 90 Fahrenheit or 32C or 86 Fahrenheit. for the European evaluations. The interior temp is very, very similar. Another thing that's a big difference is they have a different incident solar radiation. So they actually compare using different incoming heat values. So you will find different numbers, even with that seemingly simple calculation. So as with U value, NFRC solar heat gain is a whole window value. So that's an important difference since center of glass values are higher than whole window values because of the opaque frame area reducing solar heat gain when you look at the whole window. So NFRC evaluates the whole window. The European ISO can evaluate the whole window or center of glass. Passive House only evaluates from a center of glass. Now, does size matter? What's interesting when you take a look at the NFRC evaluation method, smaller windows will generally tend to perform worse in energy evaluations or heat loss evaluations because there's less glass, and the glass typically outperforms the frame. So windows that have smaller frames will actually look like they perform better in NFRC because they have a higher glass to frame ratio. But those small frames are likely to have poor thermal performance. So that's probably not what you're going to be looking for if you're designing or building to a higher performance standard and paying attention to surface temperatures, condensation risk, that sort of thing. And the size that the products are evaluated at, if you take a standard window size, NFRC only uses this specific size, this narrow little, arrow slit window, versus the Passive House so the 23.5 inch by 59 inch NFRC standard window size. The Passive House International standard window size is 48.5 inch by 58 inch. And in my experience, that's a much more realistic to project delivered size. So I think you will get a more realistic value from a UW using the Passive House method. A couple of numbers to it. You may find this interesting. So these two different windows, window A is actually a fairly standard North American frame. It's about a 27% frame in the evaluation here, with quite a different number, with the U frame being a 1.5 watt per meter square Kelvin UF versus window B having a 1.25 value. They actually end up being the same overall U value with very different frame performance, just because of that kind of disadvantage. You can see how much more the frame takes up of the whole. So what are the differences in the evaluation methods, and what impact does that make? So, I think it's important to ask yourself the question of what U value have you been given? NFRC is actually intended to provide a direct comparison between windows at a standard size. It's not a specific product performance for projects. It's apples to apples. PHI methodology is specifically designed to provide specific heat flows for products at actual size for specific performance projects. So very different intents, and as a result, different outputs, different results. So now that we've taken a look at how we evaluate window performance, let's dive into the question of glass panes. Single pane, it's one piece of glass. Dual pane is not one, but two pieces of glass. Triple pane, I'm going to let you all take this one. So what is the difference between an IGU with two pieces of glass, one coat of low E, and an optimal cavity filled with argon over on the left, and an IGU with three pieces of glass, one coat of low E, but but squeezed into the same cavity or same space as the double pane unit. The double pane unit significantly outperforms triple. So the takeaway on this is that we should never assume performance based on the number of panes inside an IGU. There is quite a bit more to it. Low E coatings are critical to reflecting heat back to the source in a glazed unit. They're not the sole determinant to performance, but they are very important. So if we take that triple unit and we add a second coat of low E, will it now magically outperform the double pane? Nope, it's still bad. But what if we optimize the cavity in the triple unit with one low E? Actually, yeah. It's about 25% more thermally efficient. It's not amazing, but it's quite a bit better. The increasing that cavity depth is more important than adding a second layer of low E. But optimizing the cavity with the 2 layers of low E, boom goes the dynamite. What happens if we add thicker panes of glass? That's actually going to be problematic because that's going to drop the cavity depth, and that's going to decrease the unit performance. So thicker glass, which can be very handy for acoustic performance, can be problematic for the overall thermal performance of the unit. So obviously you can see that different things are intertwined. It gets very complicated, and it can take a little bit of a balancing act at times to come to the right decision. Now, what happens if we add an additional coating of low E on each unit, giving us 2 layers of low E on the double glazing and 3 layers of low E on the triple? Now we get something really intriguing. When we put a reflective coating on the interior surface of the glass, if you look at the, this large version on the right, you can see that low E coating, it's a reflective point. It's actually in front of the glass. So we're stopping the heat before it can enter that pane of glass on the interior side of the window. So that actually affects the temperature of the glass. The glass doesn't get heated up by the exterior, it gets heated up by the interior. The surface temperature will drop. And by how much? So this is a snippet from ASHRAE C080 by Hamid Hyderali. He has done some really great work on detailed analysis of interior surface low E coatings in a real space. So he incorporated dynamic flow analysis, whole room modeling, varying window placement, different heating types, areas of heating sources, that sort of thing. It shows the realistic effect of interior surface coatings on surface temperatures for double and triple glazed units. This is a result from one specific model showing only the window itself, but it's indicative of the typical results. So what this is showing, you can see on here the glass. It's showing frame and then glass, and they have this area called glass edge, which is the colder part of the glass. Part of what he was able to demonstrate in this analysis is that what NFRC considers to be glass edge, the colder part in the top in this light green, actually needs to be expanded at the bottom of the glass. That's that light blue. It's quite a bit larger of a cold area at the bottom of a window. It's not constant. The red line on here is a triple glazed unit with 2 coats of low E, so it does not have interior surface low E coating. And the dew point at 50% RH is 10.2 degrees Celsius. And you can see the entire window, other than just the very bottom, maybe a 1/4 inch, all of it's above that dew point. The green line is a double glazed window with low E only on surface 2. So that's 1 coat of low E. And that one is staying above the dew point other than just the barest edge at the top and a little bit, maybe an inch down at the bottom. So this is a very warm, and the vast majority of the window is at 14 Celsius or higher. So this is a warm surface with no risk of condensation. But the double glazing with a fourth surface low E coating, all of a sudden you can see at the very top edge of the window, you've got a short area that is slightly above that dew point, but almost all, excuse me, the balance of the window here is actually going to be below the dew point and have a risk of condensation. It's also an average center temperature of 9.4 degrees Celsius, which unfortunately I can't remember the off the top of my head. What is that? 45, 50 degrees? Yeah. Um, but regardless, it's significantly below that radiant asymmetry sensation point. So this glass will feel cold. This is another study done. This was from BC Housing, a home in Vancouver. So this one isn't about interior surface coatings. This one's just about the effects of high gain glass. So to be able to achieve high solar heat gain coefficients, generally you have to reduce the reflectivity of your low E coatings. So you will see some slightly higher temperature variations on a regular basis. The glass will be a little bit colder in the winter time versus a high heat rejection IGU, and it will be considerably warmer in the summertime, obviously, because it's allowing lots of solar heat gain. So this is for a home in Vancouver, which has a ridiculously mild climate by Canadian standards. And it actually shows that that the interior surface temperature of the glass will range from 10°C, 50 degrees Fahrenheit, to 35°C, 95 degrees Fahrenheit. Our sense of radiant temperature is actually the dominant factor in comfort. That has been shown to be somewhere between 40 and 50% of our sense of temperature. So this is going to have a significant impact on occupant comfort. Air conditioning is unlikely to affect those high temperatures, nor is the furnace going to affect the low temperatures. And our aim should not be to use heating or cooling to override the effects of what is possibly a questionable glass choice. And then because when you purchase a window or door, you're not just purchasing an IGU, you've got a frame, and that matters as much or more than the glass does. So a low U value does not guarantee any of the following: airtightness, durability, embodied carbon, affordability, water resistance, comfort criteria, U installed, hygiene criteria, or structure. In fact, low U values may be an opposing concept to some of these, like structure. And so it needs to be carefully evaluated on a project by project basis. When we focus only on the IGU or the U value or the solar heat gain, we overlook other important performance metrics. So in today's presentation, we won't dig into all of these topics, but we're going to quickly address the following: airtightness, embodied carbon, affordability, comfort, and the installation U value. No matter your performance targets, airtightness should be part of the evaluation criteria for the windows and doors, and arguably one of the most important. It's entirely possible that a window with very good U values has terrible airtightness. U value isn't a metric of overall quality. It just measures the heat flow. And it typically measures it just in a simulated form. So don't forget, it is possible for operable windows to achieve airtightness values that are the same, or in some cases better than fixed windows. So unless you plan to design or build with only fixed windows, make sure to pay attention to the airtightness for both the fixed and the operable. Um, Now, embodied carbon. This is a very important consideration. If sustainability is a true goal, this is another metric to consider and balance with all of the others. It's important to balance the embodied carbon with the future reduction of operational carbon over the lifespan of the project. Um, Now, we recently published our EPD, our Environmental Product Declaration. So this is a chart that compares our products in orange to industry averages shown in blue. Um, Adding a third pane does impact the embodied carbon. In fact, glass is the largest source of embodied carbon in the window, as it's actually the heaviest part of the window. Operating windows also have a greater embodied carbon than fixed due to the additional sash. There's more frame, there's a hardware input, there's much things to go into it that increase it. But you can see the numbers I think are fairly interesting and were a little bit surprising to us, to be honest. We came out looking a little bit better than we had hoped. I think it's great. Um, Triple pane windows and PHI certified windows are most likely going to be more expensive than the average window. So, affordability can become a question. Better performing products cost more, but are they always necessary? So, in our quest for low U values and better buildings, have we lost sight of evaluating window requirements on a project-specific basis? Let's take a look at two very different projects here. So on the left is the four-story Mercy Greenbrae apartments in Lake Oswego, Oregon. This is a 100-unit, 100% affordable housing development. It's a high-performance building that is FIA certified. On the right is a single-family duplex in the city of Vancouver. It's still in the design phase, and it plans to meet the Vancouver Energy Code via the performance path, which requires a TEDI of 20 kilowatt hours per meter square annum, glazing maximum U value of 0.25, and greenhouse gas intensity max of 3 kilogram CO2 per meter square annum. Both projects carefully considered and balanced their project requirements with their budgets. So the Mercy Greenbrae apartments were able to meet FIAS targets with our dual-pane window system by ensuring that the wall and roof assemblies met the required standards and by achieving very high air tightness targets. We'll put a link in the chat that digs deeper into this project. On the right, a different decision was made. The team plans to use our PHI certified windows and doors for their project, even though it's not going for a passive house certification, as they found that they could reduce the costs on the wall assembly by specifying windows with very high thermal performance. So while they're going to spend more on their windows, overall, they're going to save money. So for me, this shows that the pre-construction energy modeling is critical, and there really isn't a one-size-fits-all window or general building approach. It really depends on a host of other variables, from the project location, the wall assembly, and code or certification targets. Now, jumping into installation. Can you affect the window's overall U value through the install position and method? Well, absolutely. And as you might guess, it also means you can negatively impact your U values. A few years ago, we asked RDH Building Science to model 6 different wall assemblies with our Defender 76 TS system, and the results were interesting. Notably, the optimal position of the window varies based on the wall assembly. You can see that in the second column here, optimal position. And the optimal position will vary depending on whether it's over-insulated frame or non-over-insulated frame. So you can see that optimization shift. Sometimes it's the same, but sometimes it is different. Over-insulation, the frame can affect this. So we have a perfectly optimized window install. The window after installed is exactly the same as it was beforehand. So uh, we also have a window that improved after it was installed. Once that was properly placed and slightly over insulated, the total value of the window actually improved. Um, we have a significantly worse window after install. That is in my opinion, that's a terrible jump. 38% decrease in thermal efficiency is massive. This one here, we have kind of a poor install compared to its optimized version. That's a 22% difference between the two. So it definitely uh, pays dividends to pay attention. Um, it's still not great, unfortunately. And I think so that last one, what I'm trying to show here is this wall 6, even though it's not great. Um, oh, yeah, I put the box in the wrong spot. Sorry. I wanted to show the the optimized over insulated the best you can get on wall 5. You can have non-over insulated versions on these top 3, the wall 1, 2, and 3. Um, those installed values are quite a bit better than wall 5, the best you can do. So uh, that probably means that wall 5 is a problematic assembly when it comes to the openings. So even though the wall itself actually looks very, very good, because it has difficulty in detailing, it means that you're going to have difficulties in delivering a project that performs the way that you hoped. So what these different wall assemblies are, we've got 2x6 with 2-inch exterior insulation, R22 plus effective. Next to it is a 2x6 steel stud with 4-inch exterior insulation, R20 plus effective. This one I think is really interesting to throw side by side because you can see um, using wood framing, 2 inches of exterior insulation, your R22 plus, wall 4, same size wall, but you have to throw 4 inches of exterior insulation on and you're still only R20 effective. So it makes a huge difference to just change one component from wood to steel, for example. Um, and then we have here, so the wall 6 is an exterior insulated concrete wall, well, ICF, 8 inches deep with, oh, sorry, it's not actually ICF. So it's just an exterior insulated concrete wall with some steel framing on the interior. And then we have a double stud, deep stud, R40 plus effective. The optimal placement between the two of them. So on the concrete wall, the optimal replacement is actually the outer position. So the addition of the over insulation greatly improved the thermal performance of the installed window. There's that very visible weak spot in there. But on that double stud, deep stud wall, you can see that the optimal placement is in the middle, and the main reason for that is the performance of the wall itself is quite high, and you don't have that same little weak point showing up at the outside of the window. Over insulation is almost always a good idea. It's great, but again, that can depend from project to project on how easy it is to over insulate, what's that cost going to be, and how much does it really improve. And while we're focused on U values and solar heat gain, it's important not to lose sight of those other performance metrics, or worse, to assume a higher quality or performance as a result of a third pane. So each of these in a singular metric of performance that can affect each other, but by no means should any window be specified or compared solely on one metric. Finding the balance for each project is key. That balance will most likely differ based on the project's unique requirements, of course. So you'll have performance targets, climate and geographic conditions, budget, and aesthetic considerations. There we go. So that's the end of the presentation here, and I'm hoping that there's going to be a couple of questions.
Hey, Mike, excellent stuff. Zach, do you want to go to
No, you're I'd say take it away. We got some questions.
Oh, good. All right.
sorry, guys. Up first, we got Grammar and Graham, over to you.
I asked two questions, but I think the first one was about outdoor boundary condition, if I'm not mistaken.
Okay.
So my understanding, and correct me if I'm wrong, which I may well be, is that the choosing 0 Fahrenheit for the outdoor boundary condition favors a narrower glass package because of the convection overwhelming the insulating value of that. And I mean, where in the country do we have 0 Fahrenheit for any appreciable amount of time? So how do you justify, or what's the justification for choosing that basically the European windows perform better because they're tested at a more realistic temperature? Isn't that right?
I mean, that's definitely a climate zone specific question. There are some pretty vast swaths of both Canada and the United States that do see very low temperatures on a regular basis through the winter. So I would say that the -18 is realistic for a lot of those areas. Of course, if you're talking along the very highly populated East Coast, that's probably colder than necessary, but it would be, I think for the Northeast, it's going to be a realistic extreme test. You would say you will hit those kinds of temperatures. So it's worthwhile to know what that heat loss is going to be when those temperatures do go that low. And in Vancouver here, we don't have to go north very far, and we don't have to go very far east before those kinds of temperatures are fairly realistic. So that's the standard that North America landed on for the testing. And whether it's the more realistic one or not, I think the important takeaway is that system is there. That's actually the one that's required by the government. The NFRC standard is in building codes of both countries. So when you have a North American manufacturer and you ask for a U value, typically they're going to give you that NFRC U value. And if you ask for a U value from a European window company, they're normally not going to give you that. They're going to give you either the European Central Standard or the PHI standard.
Excellent level of detail there, Mike. That's great. Graham, did you want to ask your second one, or are you okay to come back in a bit?
You can just
All right. Right. We'll keep moving along. Over to Mac. Mac Stickney.
Hi, nice presentation, thank you. I was curious, we have this battle with European, Canadian, and American manufacturers where we're not sure how much we can push them or expect them to divorce like visual transmittance from solar heat gain from U value. I was wondering how much we can expect to do that, how much we can push, or if you have some manufacturers that can divorce these things. Glass manufacturers versus unit manufacturers.
Sorry, I didn't 100% follow. What are we trying to divorce?
So typically, like your visual transmittance might go down with some manufacturers if you have a higher U value of the window. I was curious how much we can expect manufacturers to decouple those things. the
Oh,
visual transmittance from the U value, or solar heat gain coefficient. You know, like with commercial, we have to, there's parameters for how low that needs to be.
yeah.
How much we can expect that, if we can expect that, and if we can decouple these things. If you had manufacturers that you could recommend that are able to be a little bit more surgical with how they're applying visual transmittance, solar heat gain, U value.
Yeah. So, yeah, that makes sense now. Yeah, my brain just went down a totally different track when you first started asking the question. So, okay, so that is actually a really good question, and that's probably one of the biggest issues for most window manufacturers, glass manufacturers that are out there, is that a lot of the results of glass happen because of specific physical properties. And you can't really decouple them in the way that I know a lot of designers would like to. It'd be awesome if you just had like little radio dials and you could, okay, I'm going to crank up the VT, go down really low with U value, and then really high with solar heat gain, and it'll be perfect, and we'll get this thing. But it's always a balance. The low E coatings are actually just reflective. It's a silver oxide coat that they may put one pass, two pass. It's a sputter, like just this very thin coating. So 3, 4 passes, whatever it is, every time you put a pass of material on the glass, it becomes more reflective to energy. But it's also more reflective to light. So more passes equals darker. It's natural. It also is, so it's more reflective to heat. So it will get a better U value, a lower U value. But that means it's also going to get a lower solar heat gain coefficient, because if it's reflective to heat, it's reflective towards the exterior and interior at the same time. So it's very difficult to attain clear glass that will actually have some level of performance. There can be differences where like the amount of chemicals, not chemicals, but like minerals that are in the glass will make it a little bit darker naturally. North American glass generally tends to have a little bit of that greenish tint because of iron content, and the Europeans have a little less iron in their glass, and that does affect the clarity and some of the numbers, but it's very, very marginal. The vast majority of the effect on the glass is from the coatings.
Thank you, Mike.
Mike,
Problem?
you know what? We got new stickers. It depends.
I love that sticker. I need some of
Yeah.
those.
Yeah. When we have more of these ones that dive into a lot of the details, I'm going to be pulling that sticker up all the time now. Great question. Again, a lot of detail between Europeans and Americans, North Americans for different windows. So great job, Mike, with breaking that one down. Graham, we're going to go back to you. Graham.
Yeah. Well, I'm gonna ask my second question, then I'm gonna ask a follow-up question to my first question. My second question was, why not include air leakage in the thermal performance rating and testing of windows?
That's a great question. I think it's probably just because they are so different. They just have different testing standards that cover that, and it would probably be overly complicated to try to include that in terms of the thermal performance of the window. Most of them are simulated, like Passive House, for example. It's only done through simulation. NFRC, they simulate and they do hotbox testing, so it's got physical verification. In North America, at least, we have the NAFS standard that covers air, water, and structural. So you do have this overarching governing air tightness that allows you to compare very easily.
Oh, and my follow-up question to the first one was, are you suggesting then that in North America, North American windows are preferable, actually higher performing than European glazing? Like, are we using the wrong glazing, bringing European glazing to North America?
Well, like Sean's sticker. Um, so it is kind of interesting that there's a general perception that European windows are better than North American windows, and in an awful lot of cases that would be true. There are a lot of windows that are very well made as a minimum standard in Europe, and they're a little bit ahead of North America in terms of the adoption. They started adopting better window technologies earlier than North America did. But North America has a lot of great innovators and creative industry, and we've been doing a lot of really interesting things. And we also got hit with some the leaky condo crisis was great for the long term of North America. Our understanding of building science and our understanding of the needs of materials rapidly advanced, through this devastating occurrence for a lot of homeowners. But a lot of the testing and regulations in North America have been improving because of what happened in the Pacific Northwest here. So we actually have some of the most rigorous rating standards in the world. So when you compare a window that performs at the top level in North America to a window that performs at the top level in Europe, realistically, side by side, you put it through water testing and stuff like that, the North American windows will edge them out. We have the more you test something, the more you will learn about it, and the better you can advance it. And we do more testing here.
Thank you.
Yeah, great answer there, Mike. Again, dealing with a lot of different climate zones. Again, there's lots of different things to factor, and Florida's fun weather definitely push things when it comes to tornadoes and water infiltration. And our lovely history of the leaky condo definitely taught us a few things too. So great stuff. All right, moving along. I think the next is David. David, are you still with us?
Yep.
Go ahead.
You were talking about optimized window locations. How do you determine what would be the optimized window location in a wall assembly?
As far as I know, the best method is to thermally stimulate. So using like Flexotherm, something like that, to test the window, do some iterative design, like just check the window and see how it performs in different locations and with some different variables around it. So check it if you insulate a little bit on the outside, a little bit on the inside, you can try a couple of different things and come out with a favorable result, hopefully.
I guess I got one more question with that. So if the window is not a flanged installation, did those tests that they do, did they look at whether or not they air sealed as well and controlled condensation as well in that space between the edge of the jamb and the frame? Because that seems to be the weakest point. And if it was, in different locations in the wall, it looks like the condensation potential would be greater and the air leakage could be greater depending on how it was installed.
Well, generally, we would prefer to see some form of insulation between the window and the wall in the installation cavity. And some level of over insulation is going to have a pretty significant difference or significant positive impact on both the window and that installation. In terms of water and air tightness, we have done a ridiculous amount of testing over the years. All of our commercial projects are tested, 6 ways from Sunday. And the seal on the backside of the window frame is significantly better than a face seal on average, across, especially high-rise projects. The face seal takes a very careful detailing and you know, in a residential application with overhangs, it's a completely different consideration. That makes sense to me. But a back seal, typically with backer rod and caulking, is what is the most tested one that we see, and we see the most positive results on a regular basis.
Thank you.
Thanks, David. And we got another David in the queue. David Fujiwara, you're up next.
My question was answered. I was looking for cross sections, and you gave 6 good cross sections there. I hope they show up in a recording or whatever.
David, you definitely need to see one of the go to a trade show with Innotech. The mock-ups they bring are amazing. They're very detailed. There's got 4 of them, different types, and boy, they just nothing really beats some of their mock-ups. So if you can't see it, I'll send you a little link here to a video I did recently at another conference, and boy, very good details. So
Hey, Sean, just to interject, we do have a copy of the slide deck, David. So I'll include my email address in the chat, and you can just email me and I'll send you the deck. And anybody else who wants the deck, go ahead and ping me and I'll do the same.
Terrific.
Yep.
yeah, no, David, they again understand where their windows need to go and how some of the installation methodology needs to be incorporated. And they do a great job teaching builders how to build better, not just installing the windows, but those little finer details that make the window that much better. So, all right, we got Brigitte. Brigitte, are you still with us?
Oh, yes.
There you
Well,
go.
it was just a basic question. I love the graphics, and I'm in a wall assembly right now, and I find it interesting to see the relationship of the window and the wall and all the insulation, how it affects. I was just wondering, is that your internal software that you use, or do you know what they're similar that we can start using and show the clients how we can do better walls and yep.
Yeah, no problem. So those simulations that you saw were done by RDH, and they used Flixo for that, and we actually do use Flixo internally now as well. So evaluating our windows, we have done some installed evaluations. We find that particular software works very well for us. It is, you know, it has a cost as opposed to Therm that I believe is free. But I think the time that it takes to learn and develop something, the Flixo tends to be fairly intuitive. So that's our personal preference.
Mike, you want to just repeat that technology? I think it's Flixo, but just there's a quick question in that area. Ed May answered it, and of course it was answered by Ed May. Awesome. Well, I think that is all for questions, everyone. And we're kind of getting close to the top of the hour. Zach, is there any other comments or points you guys want to talk about?
No, I don't think so. This has been amazing, and what a great audience and awesome questions. And Mike, fantastic presentation. Really, really interesting insights that you're sharing with everyone. I think you got a lot of people thinking in new ways today. So we really appreciate that. Is there anything you'd like to share before we wrap up?
Oh, sorry, I'm hearing somebody's
Oh yeah, yeah.
You're getting all the thank yous, which you deserve. So that being said, everyone, we're gonna do a bit of a fun event. If you still have time and you want to see what's happening at Greenbuild, and if you do have an Instagram account, I'm gonna go live on the Passive Accelerator Instagram account. Probably about 5 minutes. It's just kind of run down to the expo floor, and we'll give you an idea of what's happening at Greenbuild. If you've never been to it, it's been about 12 years since I've been to one. Things have changed. And it's pretty exciting things, especially as we're working towards zero carbon buildings. So pretty exciting stuff. So Mike, Jessica, fantastic. Always appreciate all the hard work that Innotech is doing. Love the mock-ups. And again, you can get Mike to a dueling piano bar. Boy, takes takes his level to a whole another event. So
No
he's a
kidding.
well-rounded
Oh, thanks.
individual.
Multi-talented.
Well,
All right,
yeah.
everyone.
Thanks for having me out here. It was a pleasure.